an associate professor of geodesy in the Department of Natural Resources and the Environment at the University of Connecticut. He teaches courses in geomatics, global navigation satellite systems, surveying, geodesy, digital terrain modeling, and spatial statistics. Dr. Meyer is a member of a number of professional societies and was the past president of the New England section of the American Congress for Surveying and Mapping. And he's published an undergraduate book as well as many peer-reviewed journals. And either awaiting another presentation.
Okay, thank you very much. Thank you all for inviting me here. Just a disclaimer, I don't know anything about oceanography, graphic surveying, nothing like that. So I was a little bit surprised when Sam thought that my topic, which he's already seen at a surveyor conference up in Nashua, was something of interest to you. I was delighted to hear that. And the intersection, I guess, of geodesy is the common denominator here. This talk is put together really for land surveyors, primarily in the United States. Men and women who have a license to practice surveying. And the motivation is that essentially the National Geodetic Survey has decided it's a good idea for practicing land surveyors to bet their license that the NGS geoid models are accurate, because they're now advocating that hiding should be done in global navigation satellite systems. Okay, fair enough, but it behooves us to check whether or not that's a good idea. And so that is the thrust of this study. I thought I would say a few more words about myself to give you a little bit more context of the sort of things that I'm interested in. In geodesy, my interests are primarily geometric. And I work quite a bit with the National Geospatial Intelligence Agency, NGA, out in St. Louis. NGA in St. Louis is responsible for charting, mapping, and maintaining WGS-84. I was there last spring on sabbatical, and while I was there, some of the projects I worked on was new mathematical formulas of very long geodesic lines, both direct and indirect problem. What does the longitude do as you approach the North Pole? It goes singular, working out new mathematical formulations of that, so in fact, the function does not go singular, which is kind of weird, considering that it's a pole. We came up with a 14-parameter Helmert transformation from WGS-84 G1150 ITR00. That's finished, but for various reasons, NGA has decided they don't want to publish that, at least at the moment. NGA is in the process of releasing a new version of WGS-84. Should be able to roll that out in the next year or two, and perhaps at that time there'll be a 14-parameter transformation published with it. But in the meantime, we have carefully assessed the relationship between WGS-84 G1150 and ITR00. NGA has widely published that there's no practical difference, and the disagreement between the two frames has been at 2 centimeters or less. That in fact is true, and we can rigorously demonstrate that it's true. So these are some of the kind of things I like to do. One other thing, any Mathematica users? Strictly a MATLAB shop. One minute, right on. Mathematica has a geodesy package in it, and I wrote it. I'm the developer for Wolfram Research, who wrote the geometric geodesy package. So that's kind of my shtick. So let's talk about geoid models. Before I get started, I'd like to acknowledge the people who I worked with. This is the output of a dissertation by my student Kazi Arifudin. Kazi is from Bangladesh, and he's busy doing lots of other things. And at this particular, even though this is Kazi's research, as his major advisor, I had a lot to do with this research. So I need to acknowledge him, but at the same time, note that this was definitely a joint effort. This was not just an effort between my student and myself, but also with the Connecticut Department of Transportation. It was funded by them, and I want to acknowledge my collaborators there. Bob Barron is chief of surveys. He ran a survey cruise in the western half of the state for us. Derek Masalski is now retired. He was the Connecticut Department of Transportation geodesist, and he worked with us step by step, developing methodologies and analyzing the data. And Mr. Jay Duty was one of the section chiefs, and he provided us a lot of leveling data and checks down on the benchmarks down on the southern coast. All right, so as I said, NGS wants us to get our licenses that we can use their geoid models in order to convert from ellipsoid heights to orthometric heights and do this with survey. In order to set, not so much really the theory for this crowd, but just the notation, it behooves me to run through how will I denote the various numbers and in which coordinate systems do they live. We're talking here about a number of quantities. They're all heights, and they all refer to different datums, and they are subtly different. The basic notion, of course, is the fundamental, if you will, equation. It's going to relate orthometric heights, which I will denote with capital H's as traditional, to ellipsoid heights, little h, and geoid undulations. For the purposes of this study, we're talking about NAVD cores 96 and no other datum, just that one. So this is GRS 80 as placed by that particular reference frame. But the orthometric heights, there's going to be three different types of them. We are interested in using GPS to come up with NAVD 88 orthometric heights. One could conceivably use other geoid models like WGS 84, but whatever orthometric height you would get out of using WGS 84 would not be NAVD 88, whatever it is. At this point, it probably wouldn't have a name. By law, if you will, NAVD 88 is the vertical datum of the land. And so this is the vertical system that we want to have our heights referred to. We have two different geoid models, GEOID03 and GEOID09. And so you will be getting orthometric heights from both of them. To discriminate between them, I use this notation here. I'll be taking differences between the orthometric heights that I got using GPS and the truth, if you will, from NAVD 88. I'm going to take it in this direction so that the arithmetic sign is indicative of the change. So if you see a negative number, that tells you that the number that I got out of the GPS is lower than the equivalent from NAVD 88. This was a big GPS on benchmark campaign, and by big, we're talking 70 benchmarks. That's actually, there's certainly studies that have occupied more benchmarks than this, but as far as density goes, Connecticut is really a small state. You've probably noticed it. Connecticut is what sits between Boston and New York. That's our state motto. Connecticut's about this big. It's the size of a postage stamp. So even though there are studies that have occupied more markers, this is the highest density of any study that actually has ever been accomplished. So we feel that we're going to have a really good characterization of the geoid in our state. All of the markers that we occupy have NAVD 88 heights on them, and they're all first order. However, we have 4 stability classes. For those of you who might not be completely familiar with the NGS stability class, a Class A marker is one that's set in ledge or bedrock, not expected to move. So inasmuch as anything on the solid earth doesn't move, which we all know it all moves a lot, as much as anything doesn't move, those are stable markers. Class B are deep rod markers. Is there anybody who doesn't know what a deep rod marker is? Don't be shy. Okay, so as Simon mentioned, I got my PhD at Texas A&M down in the alluvial plains by the Brazos River. If you want to set a benchmark, the whole idea is for the thing not to move up and down with ground motion from the dirt, from frost heave up here, just different amounts of groundwater saturating the soil causing it to move. So what you do is you get a stainless steel rod. It's a 1/4 inch in diameter. It's about the size of your pinky. And it's a 10-foot section, and you get a big hammer, and you pound it into the ground. and it'll go all the way in, then you screw in another 10-foot section, and you pound that into the ground, and then you get another 10-foot section, and down you go until it stops. That's called driven to refusal. The rod will stop for two reasons, one of two. The first is it hits a big rock, and if it does that, you drive it a couple feet more to make sure that it's not a small rock that you can just break into, because you don't want it to be in a small rock. But if you drive it a couple feet after it stops, and it really stops, then you make the heroic assumption that's bedrock, and you call it good. Now down in Texas, to get to bedrock, you pretty much got to go through the core and on the other side. So the other thing that will cause a rod to stop is friction. There's a lot of sand. It'll stop it with sheer friction. So that's called a deep rod benchmark. That's a stability class B. Class C is the type that you may have or may not have seen by the roadside, where you've got a poured in place concrete pillar and a cap set in that. Those are not usually driven to refusal. Those are typically set by the Department of Transportation for the purposes of building roads and railroads and things such as that. And they're not as stable a monument as the other two, generally speaking. Class D are often set, for example, in the sides of a bridge or a dam, things like that. They can be very stable, but they don't fall into the other categories. While we were cruising around, there's actually a Class A marker on the top of this thing's head. There's a lot of interesting survey markers in Connecticut. Some of the ones that we recovered are underwater most of the time. They're across from the submarine base, and they're in the Thames River. For those of you who are not familiar with Connecticut, it's not the Thames, it's the Thames. Thank you very much. So, yeah, we had some fun with that. Now, one of the things, I'm from New Mexico, right? One of the things that I realized, if you're from around here, you probably already knew this. What I discovered when I moved here is trees grow here. No, really, they do. And they weren't even planted. I'm talking like grow wild, crazy, like this stuff here. And it turns out that the foliage interferes quite a bit with global positioning system satellites signals. And if you get too much of this, you can't occupy these, which, like this one, often sit right under the trees. And in that case, what you do is you create a thing called a transfer. I'll talk a little bit more about that in a second. This is our network. So down here, this is New York City, just about. There's the coast. Here's the highlands on the west. The border with Massachusetts runs right about here. That's the border with Rhode Island. And these are all of our stations. For control, we use continuously operating reference stations provided by the Connecticut Department of Transportation mostly, but we also include the Rhode Island Core Station and the one in Hampton. Where is that? Is that in Springfield? Hampshire, right? Anyways, it's close to Springfield, if that isn't exactly what it is. All right, so this is our network, and that's 70 stations. There they are. For these transfers, if you've got too much foliage obstructing the mark that you would actually like to occupy, what you do is you build a temporary benchmark nearby. And in our case, what we did was we cut a 4-foot-long piece of rebar, drove it down into the ground. You get a 2x4 and smash it down into the ground, and then you take a grinder, you take a grinder, you dome over the top, and drill a little divot in there so you've got a place to put the tip of the range pole. Then you're going to run levels from the bench to the transfer. And in our case, we used an instrument that's called an ATG1. This is sort of an old school level. It's 3-wire, but it is geodetic quality. And we actually had a micrometer. Has anybody ever run levels with micrometer? Very impressive, very impressive. For those of you who haven't, this instrument with that device on the front of it has a least count of 1/10 of 1 millimeter. So you're able to run very tight loops with this. And in fact, we demonstratively, our longest line was something, we double ran everything twice. Once when we set it and once after we were done with it to verify that it didn't move, and we could demonstrate that we had better than half of a millimeter closure error on our longest line, something like a kilometer double run. So even though we only ran according to second order protocols, and the reason they were second order is because the first order protocols require things like exotic meteorological stations that we didn't have access to. But other than that, these were first order protocols. This achieves first order accuracy. So we did not compromise the quality of our stations when we constructed our transfers. So for the occupations, it took us 2 summers to do this. Here's a typical setup. This is a GEOID receiver. If any of you are familiar with GEOID, they look like little space alien lures, little green things like this. And again, there really is no way to avoid setting up under the trees. It's impossible. If the sky was completely obstructed, then there was no point in trying to observe from that station, and a transfer was called for. But in this case, for example, the sky was, who knows, maybe something like 40, 60% obstructed. This is not ideal, but it is conservative. Fact of the matter is that trees are unavoidable in New England. And so we wanted to do a realistic study, something that a practicing surveyor could look at and say, I believe that when I do my occupations, I'll be at least this good, maybe better. And so the results that we show should be applicable. So this is a fairly typical setup, and as you can see, this was done on the leaf-on condition, which is again conservative. It would be recommended to not do that, but you might be forced to. And in any case, students don't work unless the leaves are out, right? And we work in the summer, so I didn't have any choice. That's the way it goes. For our occupation protocols, we have ridiculously long occupations. We had a minimum of 4-hour occupations on every site, repeated at least twice, and in some cases as many as 6 times for critical juncture points, where we were tying the state together east to west. That occupation duration is the specification in the NGS guidelines on how to do this. That's why we chose those times. Those are undoubtedly much longer than any practicing surveyor would do. But nonetheless, we followed the guidelines. For each 4-hour occupation, I had my students break the equipment down, put it away, and set it back up again, making sure that the instrument had been rotated 90 degrees each time. For a heighting survey, we're using fixed height rods here. Now, anybody who's used a fixed height rod knows that the centering error on a fixed height rod is almost always going to be, on average, worse than what you can get with an optical plummet on slip legs. And for a heighting exercise like this, the centering error really didn't matter that much, but nonetheless, just for good protocol, I wanted the students to follow this, both so that we would get very good horizontal coordinates and to get independence of measurements. If I just set up the receiver and let it burn for 4 hours, I get one long autocorrelated data set. It's better to break it down, set it back up, and get 4 independent 1-hour occupations. There's more information in 4 1-hour occupations if they're independent than there is 1 4-hour occupation of autocorrelated data. So this would presumably improve our results. This is the equipment that we used. In my shop, we have both TopCon receivers and GEOIDs. GEOID, that's a family name. He started out working for Trimble, and he was one of their engineers in the first Trimble receivers. And he quit Trimble and he started Ashtec, his first name. His name is GEOID Ashche, so he named Ashtec after himself. That's why it's called that. Then he sold Ashtec and he started GEOID. That's his first name. So this is his third company, and now he's got a fourth because GEOID was bought by TopCon. So this guy is a world leader in the design of these receivers. Department of Transportation, they use Trimble 5700s with Safran. Everything was 2-meter fixed height tripods per specification in NGS. Okay. So, what do the geoid models look like? On the left, we have GEOID03, and on the right, we have GEOID09. Now, to my eye, I can't see any difference. I don't know whether you can or not, but I can't actually see any difference. Now, there's some formatting differences that you can see, but as far as the shape of the contours, if you will, I can't actually tell any difference. Now, this is a good thing. This means that these two models, at least in broad strokes, aren't very different. They better not be. They're supposed to be, in some sense, basically the same thing. Well, you're supposed to represent exactly the same thing. Technically, the distinction between 09 and 03 is that 09 is higher resolution. So in broad strokes, they better look similar. And in Meyer, at least, they do. But in order to see the differences, if we subtract one from the other, the differences actually become apparent. Up here in the highlands, what we in Connecticut call mountains, in our mountains, you can see as much as 6 centimeters of difference. Down here in the Long Island Sound, same. In the middle of the state, not so much. Somewhere between up 4, maybe down 2, there's down 4. So a couple of things I'd like you to see here. The first is that one does not see any reflection of the topography of the state. That's not true here. You can see the highlands. That's what this ridge is. That's what's causing it. That's the highlands in the west. You can't see the rivers. There's not enough signature in a gravity model of this resolution to see we have 6 rivers that run through Connecticut that empty the Long Island Sound, including the Connecticut that runs like this. You can't see those, but you can see some of the topography as you would expect, but not here. I don't see any pattern to that at all, and that's good. This would suggest that the resolution, there probably isn't a lot, if any, signal in GEOID09 that was not modeled in GEOID03. So it would appear that both of these models, they're telling the same story, but maybe GEOID09 is a little bit better. This also gives us some a priori sense of how big a discrepancy our orthometric heights could be. It can't really be more than 6 centimeters different, because the two geoid models are not more than 6 centimeters different. If I go and essentially create the same information displayed a different way, I go to all the benches, and they've all got 03 and 09 heights on them. If I subtract those, how do they compare? I get a histogram that looks like this. I'm not going to show you all of the equations and all the specific numbers. We've submitted a paper to Survey and Land Information Science. It's got all that stuff in it. To me, the pictures tell the story. If you can't see it in histograms, the formulas are not going to tell you the story. So I'm going to show you the pictures. And you can trust me that the rigorous statistical analysis will confirm what I have to say. So this appears to be basically zero-centered. That's believably zero-centered. It appears to be pretty symmetric. It looks normal. Everything looks good. I do find it interesting that there is this much variability, though. I would have expected less, but there it is. So that's the setup. For the processing, the software that we use is called Pinnacle, and this comes out of Javad, but it was bought by Topcon. Now, the first thing, if I tell you that there's a difference in results, that the heights that you get out of 03 are different than the heights you get out of 09, the first thing I would expect you to ask me is, well, what makes you think your software works? So I have to demonstrate that my software works, and what I'm going to compare it against, is the NGS software, the software that they use to create these geoid models in the first place. The web interface to Pages, programmed for the adjustment of GPS ephemerides, is what the Pages stands for. Great name. It's called OPUS, Online Positioning User System. All of the observables were archived in Rhinex. Everything was processed with post-fit ephemerides. Followed the guidelines as much as we could. All of the control is active control through the core station. This is conservative again. Most surveyors would go find some first-order benches occupy nearby benches and then densify by localizing to the area of interest. That would result in much shorter baselines than we have and should produce better results. So by only using the active control, again, we're conservative. So the initial checks, how do I know my software is working? I'll check it against cores, and I'll go through those details in a second. But coming out of Pinnacle, I'm getting the baselines that were all shown in green on my slide that showed you my network. I get those baselines out of Pinnacle. Those baselines are XYZ triplets that show me the change in distance between the stations. On the core stations, I of course have published coordinates for those. So if I inverse between those stations and then compare those against the vectors I computed, they should be the same. And they were every single time. So that's good. That means that with our equipment, our software, we can recreate the NGS network. That's good. So we're consistent there. Comparison against OPUS. We took all of our occupations, ran them through OPUS, said, what do you think the ellipsoid height at this station is? Compared those against what Pinnacle told us. And this is what we got. The different colors are the different stability classes. They don't mean anything other than that. And the reason I named them different colors was because I think it makes the stability classes easier to see. So the A is a class A stability monument, C, D, there's a couple of Ds, T is for transfer. First thing I would notice is that this really does appear to be pretty much zero-centered, as you would expect or hope. So that's good. The next is I don't really see any patterns between A's, B's, C's, and D's. It would appear to just be a kind of a random mix. But look at the scale. This is just the, I sorted these, and then that's just the index of them, so it goes up to 70 here because there's 70 stations. This is in meters. Now this is ellipsoid heights. This means that Pinnacle versus OPUS, there was a 4 decimeter difference on some of these points. Now, we shouldn't really be seeing probably more than a few centimeters here, one would think. These are way, way out of bounds. What happened on these points is that those were the points where the trees were the worst. And poor OPUS just quit and went home. It politely issued a little error message saying, I can't deal with this and don't even send me data like this in the future. You rat bastard. And that was it. So OPUS failed completely on these points. Other than that, they agreed pretty well. Over here, stem and whisker plot, that's those extreme outliers. We can see that the average falls inside the box. So yes, indeed, statistically, on the whole, these two agree. There's no evidence based on these data that Pinnacle and OPUS are producing different ellipsoid heights. But this is interesting in practice. I'll come back and discuss this some more later on. Looking at this a little bit more after I remove those extreme outliers, at least from the extent, I mean, they're still there. Look at the size of the error bars on these things. You can't even see the top of the error bar from there. This actually had a 2-meter error bar. So, that was good. When OPUS failed, it told you, fair enough. It's okay that it fails, but if it fails and then lies about how good the point is, that's what really creates a problem. The other thing to notice here is that basically all of these error bars straddle the zero line. That just says in a different way, there's no evidence that these things are different. Here's a histogram of the differences. With this amount of data, it would appear to be a little bit skewed off to the left. It does appear to have a little bit more negative than it does positive. And it turns out that that's true. There is a little bit more negative than there is positive. But nonetheless, the variability outweighs the discrepancy. There's no statistical evidence based on these data that they are statistically significantly different. So that's good. That means we can go forward. We have an awful lot of data here, so we can construct different networks to test, ask different hypotheses. So we constructed 3 networks to test. The first one is just how well does this work? And we're going to call that no bad vectors, because the NGS standard says, thou shalt get rid of the crap. You will look at all of your vectors, and if there is more than 2 centimeters of variability in the vector, you will exclude it from the network. Okay, so that's what we did. That's the known bad vectors. But you know what? We had a lot of vectors. There was a cubic boatload of vectors, and it took us weeks to go through the reports one at a time. No, that one's no good. I wonder where it is. Okay, it's one of these, and there's 8 vectors there. I gotta go figure out which one of those 8 this one is. This was painful to get rid of these vectors. And we said, is it doing anything useful? Would the results have been compromised if we left them in? So we did that to test. The other thing that we wanted to test is whether or not phase center variation corrections make any difference either. And I'll talk more about it. I'm not certain what this is. I'll talk more about that a little bit later. So here's the general results. It shows you the markers. The letters again indicate stability classes. If it's red, it is too high. If it's black, it's too low. With the NAVD 88 published elevation being considered the truth. 03 on the left, 09 on the right. And what I see here is very little pattern. Some of the points over here, which are black, are red over here. Not very many, but a few. So there's a certain randomness there. Some points that have big circles, these are error circles, not error ellipses, because this is one-dimensional data, these are just heights. Okay? So this is the uncertainty in the height. Some that are big over here are small over here, like this one is big here, small over there. So there seems to be a fair amount of randomness, which is good. I am not seeing a pattern here that reflects the topography of Connecticut. That's all good. Because if I did see a pattern that reflected the topography, that would tell me that one or both of the geoid models had unmodeled signal in the real gravity field. And I don't see that here, so it's good. But let's look at it more carefully and see if we can tease something else out of it. On the left here we've got all of the heights with GEOID03 plotted against GEOID09, against the differences against the truth. The 2 models seem to track each other very well in the main, but they do seem to drift apart down here, maybe a little bit up here. The bulk of these does seem to be below the line. This would say that using the GEOID models could give you, on average, a height that was maybe something like 1 centimeter lower than what NAVD 88 says it should be. We'll look at this in detail, but in broad strokes, that's kind of what you can see here. Taking a look at the same data plotted on this side, I notice that the boxes here do not cover the 0 line. And indeed, it is statistically significant that this average is not 0, and neither is this one. So there is a discrepancy between what you get out of the GEOID models and what NAVD 88 says you should get. They do not match. But that's not the end of the story. Again, just looking at the same thing a slightly different way with the histograms. With my eye, it's really quite clear. This is not 0-centered. That one, not so obvious. This one actually requires a test. Here, that's pretty obvious. Again, I'm seeing skew to the negative side. And you can see that here. Clearly, much more of these data are sitting below the line than above. Split it out by stability class. we discovered that there was no statistical difference between our transfers and our Class A's. So we kind of lumped them together the same color blue here. And indeed, they just track each other very, very nicely. There's more below the line than above, but it is scattered above and below. It would be difficult for me to look at this and draw any strong conclusions about bias with respect to the stability A markers. But take a look at the B's. I don't know if that's above or below, but basically they're all below. That can't be chance. The C's, all below, maybe one exception, and the two D's, they're below. That can't be chance. Bob Barron, Chief of Surveys, and I were discussing this along with Dave Sherman, the Chief of the Geodetic Survey Division. And the stability B's, this might argue that there was actually some subsidence. That's a little difficult to swallow in Connecticut. Settling is not. The Class C's, the Class D's, settling, that's perfectly believable. Soil compaction. But subsidence in Connecticut of this magnitude, just from a geological perspective, it seems unlikely. It seems unlikely. And yet, that can't be chance. There's no way that that's due to any chance. Looking at the box plots, they'll just tell us the same thing. Just kind of grazing the zero. It's not real strong. Excuse me, but it does not intersect it. But over here, there's no chance. There's plenty of significant evidence here that Class B's, C's, and D's are lower than what NAVD says they ought to be. So all of these results are significant, but the question at hand is it safe to use these geoid models to do orthometric heighting with a GPS? Let's keep that in mind. And when I put the error bars on all of these results, again, what I see is that the variability dominates the discrepancy. When the variability dominates the discrepancy, on any given day, a surveyor takes out a GPS. If he or she goes out and does this a lot, yes, it will probably be a little bit too low, but on any given day, they're not going to see a pattern. It's going to come out above and below. So, we don't see any cause for general alarm. And in any case, I'll show you the number in a second. This average is down by just like 1 centimeter. 1 centimeter for an absolute accuracy of an elevation is really good, actually. If we were to say, and we can, that we could use these models and get 1 centimeter of accuracy, say in Nebraska, so far away from the oceans where the mean sea level stations are. That's, before satellite positioning, that was just absurd. That's absurd. You couldn't possibly know elevations to 1 centimeter in the middle of the country. So even though this might look slightly alarming, I don't know if it does or not, but if it does, I don't see anything here to be really upset about. The 1 centimeter here just really is kind of noise. GEOID09 does appear to have a different take on a fair number of monuments down here. And so we wanted to know, is this distribution different from this one? Because it looks like it might be. So we're going to investigate that. So we're going to do an analysis of the residuals of the two models. Now, the horizontal coordinates here, what we're going to do is we're going to fit a plane through the state, and for the height of this plane, we're going to take the residuals of what NAVD 88 said I was supposed to get versus what I really did get. So, this is centimeters, and the vertical on this plane I want to fit spread over the entire state. Well, that's a nonsensical regression. The domains of the variables are too different. So the first thing that I'm going to do is normalize my horizontal coordinates. I keep doing that every time. Normalize my horizontal coordinates to -1 and 1 with unit variance, standard kind of deal. Then fit a plane through those. If the residuals have a statistically significant trend, the models are different. And that's evidence there's unmodeled real physical signal in the Earth's gravity field that was not captured by these geoid models, if there are significant residuals. We did a preliminary study. Michelle Trannies, who actually works in New Hampshire now, as a matter of fact. No, that's not true. She works in Maine. This study was published in the Journal of Surveying Engineering. We found that those terms, there was a significant constant terms, which again is that 1 centimeter bias, and we were suspicious about the slope. But this study was very limited in its scope. It was just on a 1 mile line through the middle of campus, which was actually the motivation to do the statewide study. Here, she found about 1.2, 1.5, and 1 centimeter significant downward bias. I'm sorry, these were our results. Michelle, she only had GEOID03, GEOID09 to come out with. These are consistent. This is consistent with the number that she found, and these are the numbers that we got out of our regression. So 1.5 centimeters, 1 centimeter. These are significant in themselves. And these, I couldn't test if those were different, but they are significant in themselves. But the slope terms of this regression, GEOID03 did have statistically significant slope terms, and GEOID09 did not. So what I took away from this is that GEOID09 is more realistic, it performs better in Connecticut than GEOID03 does. Since GEOID03 has been superseded by GEOID09, it's essentially obsolete. I don't see any reason to use it, and I recommend people don't. So that's the end of the first study. The second study is, do the bad vectors, according to the NGS guidelines, actually hurt me? Oops, sorry, got it in the wrong order. Talk about the phase center. This phase center variation, is that a correction that's necessary? What is the phase center? On a GPS antenna, we've got this dome. The phase center is that place in space where the antenna's electrical center is. It's the place in space the receiver actually detects the radio waves. So that is the equivalent to the optical center of a theodolite telescope. It's the place the GPS is saying, here is the place I'm going to measure the position of. GPS antennas are typically microstrip antennas, and they're active. The phase center doesn't actually reside on the surface of the antenna. It floats in space, up above the antenna. In fact, it can be outside of the radome of the antenna. I'll show you some in a second. On old Trimbles with compact dome, they can have phase center variations this large. Compact dome is about this big. So you understand the place in space where the antenna is actually measuring isn't in the antenna, it's somewhere above it. That's the phase center. The phase center moves. So here's a picture of it. There's your phase center. It's the phase center offset. With this picture, one would think the phase center is just a fixed place, but it's not. The phase center moves as a function of the angle of elevation to the satellite. So as the satellite transits the sky, the angle of elevation is changing constantly, so is the phase center. So the place that the antenna is positioning is moving up and down as the satellite goes across the sky, and it can be a lot. That's called phase center variation, and here are some plots of the phase center variation of the antennas that we used in our study. For our hyperlights, let me walk you through this antenna phase pattern diagram if you're not familiar with them. Straight up here means a zenith angle of 0 degrees. This is a zenith angle of 90 degrees, so it's horizontal. Here's the zenith angle of 45. So a hyperlight plus has an 8 millimeter phase center variation when the satellite is 45 degrees down from the horizon. When the satellite is right overhead, it's about 0, and it comes back to 0. When the satellite gets, straight overhead, back to the horizon. Red is L1, blue is L2, and you notice it can go negative. About 8 millimeters here for my legacy. This is one of the GEOID receivers, about 6. 8 millimeters for another one of the GEOIDs. For the trembles, 6 millimeters. But look at this, 20 millimeters, 2 centimeters for the compact one. That's quite a bit. These are the choke rings on the core stations. They're very small, like a couple millimeters, less really. So modern high-quality antennas really have very, very good phase center variation. The old ones, not so good. So does it matter? Yes, it does. Our receivers, we can turn off the phase center variation in the software. It turns out there's a switch that I can turn it off in the firmware as well. The receiver will do this correction in the firmware. And guess what? You have to make sure you don't do it twice. I didn't know the firmware would do this, right? So I turn it off in the software. Now it's only being done once and everything works. Going counterintuitive result there. And then I turn it back on and now it's broken. Yeah, I was doing it twice. So yeah, you have to be kind of careful about that. If you turn it off and you don't apply the phase center variation, it behaves exactly the way that you would expect it to. The results come in statistically significantly below the line. Right on the line means that everything was distributed normally, clearly. Most of them are too low. And by about the amount that you would expect. So yes, it matters. It's easy to do, so absolutely, you have to do it. The results for the all-vector network, if I take all of the vectors, good, bad, and ugly, dump them into the least squares adjustment, does it hurt me? No, it doesn't hurt me at all. The answers come out nice and normally distributed. They might have a little bit more variability than otherwise, but other than that, the answers are not statistically different. Kind of counterintuitive. This would seem to violate the garbage in, garbage out principle, but it doesn't. I'll explain why in a moment. So, for conclusions, we say both GEOID03 and 09 are accurate at their stated levels, given the uncertainty by the NGS. Therefore, they are suitable for use in Connecticut. We saw that 09 worked better than 03, but both of them are too low by around a centimeter. Maybe there's some subsidence. The chief geophysicist of the USGS happens to be on the campus of the University of Connecticut, and he was on this committee. He said that subsidence might be possible. Okay, if he says it might be possible, maybe it is. Post-glacial rebound, I don't know. But what's interesting is that something was definitely there on those deep rod benchmarks. They were too low. Those rods are 20, 30, 40 years old. That's old enough that subsidence could have happened. Space geodesy positioning techniques are accurate enough, they should be able to see it. So we don't feel that this is a reflection of these GEOID models. We think it means we have to go reobserve our network. We think our network is broken and it needs to be reobserved. That's the take-home message that we got from that. Fortunately, the NGS models did not show any unmodeled physical signal in our opinion, so there was no justification of creating some sort of a supermodel to put over the top of them, a custom home-brewed GEOID model. That, I really, really didn't want to have to do that, and I was really glad that we didn't need to. The height of the antenna is absolutely critical. Unlike a typical topographic survey with levels or a total station where the height of the instrument is irrelevant, it's absolutely a first-order quantity in the error budget for heighting with GPS. And it's hard to get it right for the reasons as I explained with the phase center variation stuff. Also, the software just made this difficult to do, and it shouldn't. We have databases in the software for the phase center variation, and the order that you put those in to the database in the software is opposite the order they appear in the NGS data sheets. And neither one of them have numbers that tell you which is which. So it's super easy to do it backwards. Not only that, for some reason, when we would bring in Rhinex files from core stations, it would erase the database and not tell you. It's clearly a bug in the software. So you go and you run all the results, you bring in today's data, and nothing works. And that's not what you think, oh, it must have erased the database. It's not the idea that just pops into my mind. It took us months to get the HIs right. And it's absolutely crucial because any mistake, any blunder in the HI goes directly into the ellipsoid heights. So getting the HIs right was absolutely crucial. Now, concerning the effect of these substandard networks, garbage in, garbage out, actually no. Garbage means inaccurate. These were not inaccurate. They were imprecise. You all know the difference between accuracy and precision. There was no reason to believe those vectors were inaccurate. They were very imprecise. Well, what happens if you have a least squares adjustment of multiple observations with different variances? The weight is the inverse of the variance. So we have very tight fixed vectors. According to Pinnacle, variance of like 1 millimeter. Not real, but nonetheless, that's what it says. And in the same mix, we've got vectors with 2.5 centimeters, 25 times higher variance. 1/25th the weight. The least squares did exactly what it was supposed to do. It took these uncertain vectors, squashed them into nothing, threw them away for me, thank you very much. They didn't affect anything. And because we had so much data, no individual vector, even if it was wrong, could possibly change the results because they were so down-weighted by the least squares adjustment. In other words, science worked. It did exactly what it was supposed to. We had a preponderance of data. Most surveyors would never spend that kind of time occupying these stations. And they would never come back and revisit these points. Hopefully they'd come back twice. 6 times, not a chance. And so the least squares had the best possible environment of data to work with that you could ever want. Would a practicing surveyor want to follow the standards? Yes, I think so. Why not? Following the standards is just following standard practice. So when you get to explain why things aren't working right in front of a judge, you get to say that you follow the rules, and that's important in a court of law. Also, for a small network, it doesn't cost anything. We literally had thousands and thousands of vectors, and it was very painful to pull these things out. Most vectors will have maybe tens. Most networks will have maybe tens of vectors. It just doesn't cost anything. So why not follow the rules? But we found it didn't actually matter. OPUS is being touted widely as being a substitute for full least squares network adjustment. We didn't see that. I don't recommend that. I don't think OPUS can be as good as Pinnacle. Why would we expect it to? Pinnacle has all of this data at its disposal. It's putting it together with least squares. It's got to be better. And we found that it was. But we found OPUS was excellent as a check. And any time OPUS was very different from what we got out of Pinnacle, we went and found out why. And there was reasons, like too much trees. OPUS can't deal with it. So last, but not least, how general are these results? We suspect that any place whose geology and geography is essentially the same as Connecticut, i.e. New England, we would expect to see the same results in New Hampshire as we saw in Connecticut, likewise Maine, probably New York, Pennsylvania, etc. Where we don't think we would see the same results as in the mountains of the West. The geoid models do not work as well in the West as they do in the East. The East, frankly, doesn't have mountains, not even the Appalachians, not compared to the rugged Rockies of the West. It's not too hard to get GPS receivers and gravimeters up on top of the Appalachians and make control observations up there. We've done it. It is very difficult to do that in the Rockies. It wasn't done. And look at how much variability is in Arizona. Look at the scales. The fact of the matter is these models really don't work very well in the West. This one is just Arizona, but I've seen similar maps for Colorado and Utah, and there's similar results. So, it's great to live in the East. Models work. I'd be hesitant to take this out and use it in the West. We've got some work to do on the geoid models out there. And they are, that's what the GravD program is all about, the flying gravimeters through the Rocky Mountains so that they can improve these models out there. All right, that's it. You have any questions? Yes.
First, a comment about the subsidence. Beyond post-glacial, if it's overpumping the ground or building a heavy monument, will cause the ground to subside.
Yeah, we discussed that, but we can't really think of any place where there's significant subterranean pumping. Connecticut gets its groundwater from two massive lakes outside of Hartford up in the Litchfield Hills, so we do not generally pump massive amounts of water for groundwater. There is a huge number, around 100,000 private wells on the east, but they're very widespread. They are fractured bedrock, but the yield on those wells is really low. So we thought about that and decided probably not. As far as post-glacial rebound, it would have to be acting very quickly. These are very short geologic times, so that didn't seem to make sense. So, and yet, my geophysicist friend said maybe, but I couldn't quite see it.
Heavy monuments and buildings might resolve that problem.
None of these were there. Yeah, some of them were quite near bridges, and we thought that possibly there was something going on with groundwater having to do, as you all probably know, we have fractured granitic aquifers up here, and so if the water is getting inside of these aquifers and expanding, it might cause something like this to happen. But it was pure speculation. We had no data to justify that, or even a good model.
And there's a question now regarding OPUS and Pinnacle. I haven't worked with Pinnacle, I worked with other software, AOS and PGO, but still there are black boxes where I'm not sure what's going on. Have you compared it to the gamut of the Bernese?
We tried to compare it to TGO, but for various logistical reasons we weren't able to do that. And I also wanted to compare it to the gamut or one out of JPL, etc. But it turns out Bernese is wicked expensive. They want like $14,000 for a license, and you've got to be in some kind of special club to get the one from JPL. And oh my God, I can't figure out how to run gamut. So we tried, but we weren't successful. Questions?
Between when NGS did 03 and did 09, they probably did more measurements in the state, right? Both in terms of setting up on Class A points with GPS receivers to better the geoid or more gravimetric measurements. Did you get hold of that stuff in terms of seeing how many more measurements that they did?
Oh, we did more, by far.
I mean actually NGS, just in terms of, because they had come up with the 09 model, which, we have to assume they, at least in Connecticut.
You mean how much more data is in 09 compared to 03?
Right, in Connecticut.
Good question. Oh, well, in Connecticut, I don't know that there's any at all.
Okay.
The major difference between those models is the pedigree from the pure gravimetric side. GEOID03 comes from EGM96 by way of, there was an intermediate USGG product in between. GEOID09 comes from EGM08. EGM08 is largely the product of the Grace and Champ missions. So there's a tremendous bulk of satellite gravimetry data that went into 08, which is why it was so much better, among other reasons, from EGM96. So one would expect 09 to be considerably higher resolution than 03, and we think that it is. We think that that tail, the discrepancy, where 09 separates from 03, we think that's real. And that's just higher resolution and better modeling on the part of 09.
Well, and did NGS come in and occupy additional stations?
We actually participated in that occupation campaign. We did GPS on benchmark to help them do this. So we know they did. There was 16 stations that we occupied for them and for 09.
And I'm just kind of trying to think of in terms of that class B, in terms of the stability classes, if any of those had been...
I don't recall any discrimination by stability class, but we occupied A's everywhere we could. We have a lot of A in Connecticut. We're really lucky because when you put up a rock outcrop against a snowplow, the outcrop usually wins. So our first order network is largely intact. And so is yours as far as I know. New England is really lucky in that regard. So A everywhere we could, otherwise not.
What's the total magnitude of the earth tide? Is it falls within this discrepancy, or is it much smaller?
No, actually, sir, as I understand it, the earth tide is like half a meter. But if you were also thinking about the ocean tidal loading, we took a look at that, and I could find no evidence of ocean tidal loading that was in our air budget, that was significant in our air budget. We happen to have a core station in Groton, and there's also a NOAA co-ops tide station across the water from there. So we went and got time series of ellipsoid heights from the core station, compared them against the actual observed stage of the tide, and we saw no correlation at all. So as far as I can tell, ocean tidal loading is a myth in Long Island Sound. But I also read a paper about a station on the southern coast of England, and this is something, if you guys know about this, I would really appreciate hearing.